Hello, everybody. So in this video, we need to go and compare or just connect different ideas we've discussed previously. In particular, we need to delve a little bit deeper into linear transformations and their connection with the rank of spaces. So if you're given a M by R matrix A and a R by N matrix B, then the matrix A times B is well defined. It's just an M by N matrix. Notice that A times B and B have the same number of columns, N. I'm going to prove to you that the rank of A times B is at most the rank of B. And actually it's equal if you know A is invertible. Now be careful, they can be equal and yet A is not invertible. It's if it's invertible, if A is invertible, then these two things have to be equal to each other. There's a very important geometrical interpretation of this equation. So it certainly deserves a proof. All right. So to start off, suppose that X is in the null space of the matrix B. Now that means by definition that B times X is 0. I want you to pre-multiply both sides of that equation by A. That means multiply on the left by A. That would imply then that A times B times X is equal to 0. So therefore, this vector X is actually also in the null space of the matrix A times B. But that means that every vector in the null space of B is contained inside the null space of A times B. So the null space of B is contained inside the null space of A times B. And obviously, the dimensions then can only increase. So the dimension of the null space of B has to be no more than the dimension of the null space of A times B, because one's contained in the other. Seems reasonable. Well, that means then that the nullity of B is at most the nullity of A times B. All right, we have that inequality. We'll need that in a moment. So now just on a side note, different track, by the rank theorem, that means that the rank of A times B plus the nullity of A times B has to equal the number of columns in A times B, which is N. But that's also equal to the rank of B plus the nullity of B, because that's also the number of columns in B. Now, what I want you to do is take that equation, and I want you to subtract the rank of B and the nullity of A times B, or vice versa, in some order. For example, if you take the rank of B minus the rank of A times B, that then has to equal, because the equation I just gave you, the nullity of A times B minus the nullity of B. But we know the nullity of A times B is at least as large as the nullity of B. So that difference is non-negative. So the rank of B minus the rank of A times B is non-negative. That can only happen if the rank of A times B is no more than the rank of B. And that's what we have to prove. This is a really neat little theorem. It just emphasizes once again how linear algebra things are all kind of interconnected. And it's useful to view certain topics one way and to jump around in the topic, to jump around between different topics, to explore some new concept. What I haven't done though yet is to show you that if A is invertible, then these are actually equal. To do that, I'm going to show you that if A actually is invertible, then the rank of B is no more than the rank of A times B. So then these two inequalities together will then imply that they're equal. That's actually really easy because of what I just proved. So if A is invertible, then the rank of B has to equal the rank of A inverse times A times B, because A inverse times A times B, that's just B. So those two things on the left and the right-hand side that you have here, this and that, they're equal just because the matrices are equal. But because the theorem I just gave you, whenever you have a product of two matrices and you want to find their rank, it's always no more than the rank of the second matrix in that product. So I have a matrix times a matrix. So by the theorem I just proved to you, that rank is no more than the rank of the second matrix in that product, which is the rank of A times B. So therefore, the rank of B is no more than the rank of A times B, which is no more than the rank of B. So therefore, they're all equal to each other. That's neat. That's a neat little result. Now, you might wonder, oh my God, why? Why is that useful? Let me show you. So You need to look at things in terms of mapping, going from a space to a space. So suppose you have a linear transformation as defined by a matrix multiplication, going from Rn to Rm. I've given you those spaces. So it takes a vector then in Rn, and it maps it to a vector in Rm, and the mapped vector is a times x, where the input is x. Okay, some notes you should probably, hopefully, be able to see easily. If you have any subspace at all in Rn, a subspace, we already know, is a span of vectors. It's just a span of a bunch of vectors. So it's spanned by a basis. Well, you can then think of that space as the column space of some matrix, because a column space is a span of the columns. It's just a different way to look at it. Okay, so then a subspace in Rn can be thought of as the column space of a particular matrix, where the columns in that matrix are what span the space. Okay, but the ith column of B sub I, it just corresponds to the ith column in the product of A times B, which is A times Bi. That means that if you ever take any linear combination of vectors in B, it will automatically correspond to a linear combination in the column space of A times B, because a linear combination from the column space of B, you can then distribute the linear transformation through that linear combination, going through the sums, going through the constant multiples, and you'd map the linear transformation to the columns of B, but that would then become the columns of A times B. So every vector in the column space of B gets mapped to a vector in the column space of A times B. That's the neat thing we need to notice, that the transformation, which is a linear transformation, a matrix transformation, which is defined by multiplying a vector by the matrix A, it just maps the vectors in the column space of B into the column space of A times B. Now, why is that interesting? Well, the column space of B and the column space of A times B have a dimension, which we call their rank. So here's the picture again. We know, though, that the rank of A times B is no more than the rank of B. This then says that the rank of A times B, that's the image of this mapping, is no more than the dimension of the original space, the rank of B. So we have that nice little result. The image of a subspace under T can never exceed the original subspace's dimension. So if you have a subspace whose dimension is 2, and you apply some linear transformation to every vector in that space, it will then correspond to a new column space. And that dimension is never any larger than the original dimension, which you all go, well, okay, well, that seems reasonable. But this is a proof of why it's true. Now, there's something else, though, here that's also really cool. It just so happens that the rank of A times B is actually also never any larger than the rank of A. And this time with equality if B is invertible. Why this is true is also really easy to explain, and it deserves a proof. So it winds up being, though, that the rank of A times B is instantly equal to the rank of A times B transpose. That's one of the statements I gave before, that the rank of A and the rank of A transpose are equal to each other. That's because when you transpose, you don't actually change the position of the pivots. You don't change any of the locations of really the leading coefficients. So that's why they should be the same. But A times B transpose, you know that when you take the transpose of a product, you reverse the order of the product, and you just take the transpose of all the factors in that product. But then, because of what I proved to you before, that's now a rank of a product two matrices. That is always less than or equal to the rank of the second matrix in that product, provided that the first, and you get equality if the first matrix is invertible. So then you would get equality if B transpose is invertible. Well, if B transpose is invertible, then B is invertible, because we know that that's from a theorem we have about invertible matrices. but the rank of A transpose is the same as the rank of A. Be using that statement about transposes again. So you get this nice result that the rank of A times B is no more than the rank of just A. And again, with this time with equality, if B is invertible. What does this mean? Well, remember that A times B is the image of applying the transformation to the column space of B, and the column space of B is just some subspace. So that means then that the image of a subspace under this transformation can never exceed the rank of the mapping itself. That's neat. So you have this nice result that the dimension of the image of any subspace under a linear transformation can never exceed the rank of A being the standard matrix in that particular mapping. I want to show you kind of with pictures what's going on. So you can see, oh yeah, that seems reasonable. So look at the projection mapping. So we're going to project things from R2 to R2. We're going to project vectors upon the line y equals x. Now, I already taught you how to do this, how to find that particular matrix. I just gave you the result. So then that's the projection matrix. So then that's the matrix in terms of a standard matrix times the vector x. Notice that that matrix, though, that standard matrix, its dimension is only one. It's because it has linear count, the two rows are multiples of each other. So the rank is one at most. But you're mapping into R2. So that means that when you map things from R2 into R2, the mapping is never going to be any larger than dimension one. So there's some collapsing going on. You start with the whole plane, and whatever you do the projection, you crush it down at least by one dimension. But you might actually crush it more depending upon what you do, what you're mapping. So to show you what I mean, here's that mapping again. Let's look at three different cases. What if you map the entire plane? Well, if you map the entire plane, that means project every single vector in the plane onto the line y equals x. Of course, you go from a two-dimensional object to a one-dimensional object. And that agrees with both of my statements, because notice that the dimension of the target space, that's this guy, is no more than the dimension of the original space. That's this guy. So the dimension here is 1, while the dimension here is 2. So the dimension of the target space, the result, the dimension of the actual image of the mapping is no more than the dimension of the original space. But then also remember that the dimension of the resulting image can't exceed the rank of the matrix. So the rank of this matrix is 1. And in here, yeah, I mean, the image dimension is 1. That does not exceed 1. So that looks good. There is some collapsing here. But what if we find out this subspace? So this subspace is a span of one vector. That vector is just not orthogonal to the line y equals x. You can then take all those vectors that lie upon that blue line and project them upon the line y equals x. And notice that here, that this goes from a dimension 1 space to a dimension 1 space. And that agrees with everything I've done so far. This is dimension 1. This is dimension 1. The two statements were that because of the original space's dimension 1, the image dimension can't be more than this. So the image's dimension is 1, and that does not exceed the original dimension of 1. Also, though, we know that the image's dimension can't exceed the rank of the standard matrix. So the rank of the standard matrix is 1. So the image can't be more than 1, and it's not. It's 1. So good. It is possible, though, to get below dimension 1. So the image can be below dimension 1. It could be dimension 0. Only way it can be dimension 0 is if the actual space is only one vector. It's just a 0 vector. To see that, take the space that it lies in the line y equals negative x. So that's orthogonal to the line y equals x. Take that blue line and project it upon the line y equals x. All those vectors on the blue line, all those vectors that would lie on that line, all get sent to the 0 vector. And this still jives with what I've said so far. The dimension of the original space was 1. The dimension of the image is 0. So the dimension of the image can't exceed the dimension of the original space. That's good. Also, the dimension of the image can't exceed the rank of the standard matrix. So the rank of the standard matrix is 1. So the dimension of the target space, that's 0, does not exceed the rank of the matrix, which was 1. So then this is all right. All right. This explains what you think. So that means then there's a couple of neat ideas you have going on here. Suppose you have in this exact same, take the exact same mapping and take, say, any space now, take any space at all. That's not the entire plane. It's either a line or a point. Take an image of a line or a point. Well, then when you map it, the result has to be no more than dimension 1, because that's the rank of the matrix. And it can be no more than the dimension of the space you're mapping. So if you start with a line, the image is either rank 1 or rank 0, because you start with 1 and you map into something that's no more than 1. It could be either 1 or 0. If you start with a point, that's dimension 0. So when you map it, it can't be any more than dimension 0. So therefore it must be 0. So in this case, mapping the origin would map only to the origin. You get, again, a lot of really neat results. It gives you a way to figure out kind of what happens in the mapping just by looking at the ranks of the different things, the dimensions of the different spaces. And I think that's enough for now. We'll come back to this idea again later on, and I'll push it a little further.